So let's solve some problem from the section on rotation about fixed axis, equations of motion. And I'm going to do a simple problem for 1757. And 1757 talks about a wheel with a radius of gyration 200 millimeters and it weighs 10 kilograms. It's in the vertical plane, it's hinged at A, pin jointed. And there is a moment applied that is linear with time, 5t Newton meters. And we need to find angular velocity when t equals 3 seconds if it starts from rest. And then we need to compute the reactions at the pin. Okay, so I started the problem, and we can calculate first the mass moment of inertia about the axis of rotation, which is the centroid because of symmetry, is the center mass of the wheel. And according to definition, moment of inertia is mass times radius of gyration squared. So mass is 10 kilograms times, and I'm working in meters rather than millimeters. So K is 0.2 meters squared. That's 0.4 kilogram meters squared. Okay, and then we're going to sum moments by writing the third of the equation for rotating bodies. So, and rotation is about the centroid, the center mass. So sum of moments about center mass is centroidal mass moment of inertia times angular acceleration. This is the equation. Center mass in our case is notation, the label is A. So the only moment available is the 5t Newton meters applied, and then I'm saying the calculated moment of inertia 0.4 times, and alpha we know it's d omega over dt, okay? So I can say 5t dt equals, not that I couldn't divide by 0.4, so better yet, I'm just going to say 5 over 0.4 t equals dt rather equals d omega. And of course what follows is an integration. We know initial conditions, so t equals 0, starts from rest, omega is 0, initial conditions. So 5 over 0.4, that's so 5 over 0.4 is 12.5 t dt, integral from 0 to 3 seconds, equals integral of the omega from 0 to omega. So what we have to the left is going to be 12 over 5 divided by 2 t squared, so 12.5 over 2 times t squared, going from 0 to 3, equals omega minus omega 0. So omega 0, this is 0, so this is omega. And to the left we have 12.5 over 2 times 3 squared equals, so it's 56.25. It's omega, and these are radians per second. So this is the answer. Now for the second part, what are the reactions at the support, at the pin joint? We're using the force equations in equation 1714. And since this is not an accelerating, we're going to just have static equations. Sum of forces in the, well, it says normal and tangential, but we're going to say sum of forces in the x direction equals 0, sum of forces in the y direction equals 0. And I need a free body diagram now. So I have the weight, mass times acceleration, and I have the reaction, the force in the x direction, the force in the y direction at A. All right. So clearly, sum of reaction at so Fx equals 0 from the second equation is the answer. And then in the vertical direction, I have negative m, assuming positive up, m times g equals, negative plus Fy equals 0. So Fy is m times g, that is 10 times 9.81, that is 98.1 newtons. Okay, answer. And this one, answer. So really, the fact that the disc, the wheel rotates, does not affect the reactions at the support. All right, so this was one problem, and I'm pausing while I'm selecting the next problem. Okay, this is actually a problem that we started in class. Problem 1559. It's about a slender rod, mass M, and it's released from rest when horizontal. It's pinned at a point other than the center of mass, which is L/3 from end A. Okay, and it's released from horizontal position, and we need to find the force at the pin B when the rod is vertical. There is an easier way to solve this problem using Chapter 18 energy conservation principles. Remember, there we have, same as in case of motion of particles. So when we have position, the integral form of the equation of motion, position is given, it's energy. Okay, so back to the problem, 1759. Well, we have it on paper. We calculate in class the distance from the hinge to the center of mass. It's L/6. And then the mass moment of inertia about point B of the rod, it's going to be centroidal moment of inertia plus parallel axis theorem would be distance bg squared times the mass. Okay, so from the table, we have here slender rods. Again, will be either x or y moment of inertia. That's 1/12 ml squared. So it goes 1/12 ml squared plus n times distance bg, we calculate over 6, so that makes for 1/9 ml squared. In terms of equation of motion, there are options. The best is to use rotation about fixed points. So really, equation 1716 might give us the most convenient way to calculate alpha and omega when the rod is vertical. Okay, so and then we can state the equations for force to find reactions at the support. In the horizontal direction, there's just the reaction of the support. In the vertical direction, we have the weight. And but again, that will be once we have alpha and omega calculated. So I said that the equation of motion will be now about the fixed point B, the pin. So sum of moments about point B equals mass, or the mass, a mass moment of inertia about B times alpha. Okay, and let's not forget when stating the equations for moments, we have, so what do we have? We have, let me just write it. So I have sum of moments, that will be the gravity, and we calculated this. I took a picture of the bore before leaving. So the arm of the force is going to be, and I need to write as function of theta, is going to be bg cosine theta. So it's bg cosine theta. Okay, the arm of the force. So I have, and we're considering positive counterclockwise for moments. So we have negative bg was L/6, so negative L/6 times cosine theta. All right, so arm of the force times the force itself, that's mg. Okay, mg. And then this is equal to the mass moment of inertia times alpha. So we have 1 over 9 ml squared. So this is the equation of motion. Now, okay, so there's something else. So we assumed positive to be counterclockwise, and then theta is measured clockwise. So unless we change and we make positive moments counterclockwise, alpha, which I forgot to multiply, will be a negative value. So negative. Okay. Or we could have considered positive moments clockwise, theta clockwise, theta dot clockwise, theta double dot clockwise, that will be alpha. Okay. So equation of motion, we can turn this into plus is L over 6 cosine theta mg equals, which can be simplified, really. So I have mass that vanishes. I have the 1L that's coming out. So this was the square. So the equation of motion is alpha equals, I get alpha from here, I multiply by 9, so it'll be 3 over 2, 3 cosine theta over 2 times L, because I'm also dividing by L. Okay, so this is the equation of, and was it G? Yes. So 3 cosine theta times G over 2L. It's theta. So this is the equation of motion. Now, of course, I can write alpha equals d omega over dt. So we would need to, is there a need to integrate? No, because it's function of, okay, it's function of theta. So we have alpha when theta is 90 degrees, this is equal 0. And then of course, if I'm to, because in the equation for forces, we're also going to use omega. So we need omega. If alpha is 0 at 90 degrees, which is expected because it's where, as the, if you can see this, so if you have a pendulum or a swing, really, a child swing, the maximum velocity is when the swing is vertical down, and that's where it starts slowing. So it comes from a swing maximum when it's vertical down, and it starts slowing down. So it's when acceleration switches from positive to negative to slow down. So alpha at 90 degrees, theta 90 degrees is 0. In order to get omega, we need to integrate. So what do we have? Okay, so since integration will be actually done not with respect to time, but rather theta, we need to use a, and we know this from linear motion. If you go to the inside cover, there is this form A ds equals V dv. Okay, so A would be alpha, ds would be d theta, V will be omega, dv will be omega. Or we can just say d omega over d theta times d theta over dt. This is alpha, and it's 3 cosine theta g over 2L. All right, so I can take, and I can make this equal to omega, or it's omega, d theta over dt. So I have omega d omega equals 3 over 3g over 2L cosine theta d theta. All right, so omega d omega and 3, okay, and this is the one that we're going to integrate. So integrate from 0 to pi over 2 for theta, and omega, it says start from 0, so from 0 to omega, and this will be omega at 90 degrees. Okay, so to the left we have 1 over 2 omega squared, and to the right I have, everything comes in front, so this will be sine of theta, 3g over 2l sine of theta, and going from 0 to pi over 2, that is, okay? So sine will be sine of pi over 2, that's 1. This will come in front, so it's 3g over 2l, and then sine of pi over 2, or 90 degrees, that's 1, minus sine of 0, this is 0. So this is equal to 3g over 2l, okay? And this gives us omega. Omega will be a square root, and it's square root of, I have 2 that I'm multiplying with, so it'll be 3g, square root of 3g over l. 3g over l. This is important at theta equals 90 degrees or pi over 2. And likewise, this was, I even stated so. Okay, so we have alpha, we have omega. We can now write the equations for forces. So I think I overshot going backwards. So the equation would be sum of forces in the normal direction, sum of forces in the tangential direction. Now when the pendulum is in the vertical position, normal direction would be vertical up, tangential position would be horizontal to the left. Okay, so let's copy these. So I'm saying sum of forces in the normal direction, it's mass times omega squared times acceleration. Okay, so times the radius to the center of mass, yes. And sum of forces in the tangential direction is mass times alpha times radius to the center of mass. And in our case, radius to the center of mass is the distance bg, which we calculated to be L over 6. So what do we have? Again, we're assuming the, maybe I should draw the pendulum in the vertical position. So I have the pendulum in the vertical position. This is the centroid. I have B. This was point A. This was point C. And so acting is mass times accelerated to gravity, yes, the weight. And then I have reactions at the supports as theta increases and omega and alpha this way. So we have a tangential direction, and then the normal direction would be this one. Okay, so I'm going to say force in the tangential direction. I'm going to say force in the normal direction, and this is ut, this is un, unit vectors. Okay, but external force would be acceleration to gravity. Alright, so the two force equations from above, I'm looking at the normal, so it will be negative mg, positive force in the normal direction, positive would be up, equals mass times omega that we calculated. So omega at 90 degrees was square root of 3 n squared, so no square root, 3g over L. This is omega squared again. So we have omega squared of 3g over L, just calculate it. And then times L over 6. And then in the tangential direction, we have So positive ut would be to the left. I'll have negative ft no other force equals mass times, alpha happens to be 0, so 0 times L over 6. So this means that the horizontal force Ft equals 0, and then the vertical force reaction at B, that is, it's going to be so the normal force reaction at the pin is going to be mg, and mg times 3 over 6 is 1 over 2, so mg over 2. Okay. Have I forgotten about the, let's see. So normal force is, I have mg. I need to move mg to the side. So it will be mg, this one, to the left, and then plus, plus mg over 2. mg over 2. So the answer is 3 mg over 2. 3 mg over 2. This is the reaction that supports. As you can see, is bigger than, so this is the answer. This is bigger than the weight of the bar by 50%. So if you just let it go and settle to equilibrium, vertical equilibrium, it's only mg, but if it's coming with a swing from horizontal position, it's 3 mg over 2. Okay, so this was another problem. Let me see. So I have, so this was first page, sort of scan with results of what we did in class and earlier in the problem. But here we stated the equation of motion about the pin, and it was much easier to solve. We found alpha, we found omega, and then stated the sum of forces in the normal and tangential direction, and got the final answer. Okay. All right, so let's look at this problem, 1776. Interesting number. So we have a 20 kilogram roll of paper, and radius of gyration is 120 millimeters. Centroidal radius of gyration. It's supported by this pin, which is B is at 400 millimeters behind the contact point, which is vertical with A. And the rolls is on the floor. We have a kinetic friction coefficient of 0.2, and there's a force applied horizontal to unwind paper from the roll. And we need to find the initial angular acceleration of the roll as the paper unrolls. Okay, so I have here a drawing with some forces shown. So we have the applied force, we have the weight, we have the normal reaction at the contact point. Does it have a name? Yes, this is point C. And then I'm going to show the reaction. The bar AB is a two-force member. There's no weight or negligible weight. So I'll have a, and it's in tension, keeps the roll from moving to the right. So this will be the force in the bar, FAB. Okay, so normal friction force and the weight. Okay, so what we need, firstly, the radius of gyration of the in mass being given, we can calculate the centroidal moment of inertia of the roll of paper. So it's going to be mKa squared. So that's, we have 20 kilograms, mass is 20 kilograms, and Ka was given as 120, so in meters 0.12, so times 0.12 squared, and this is equal to 0.12 squared times 20, 0.288 kilogram, 0.88 kilogram meters squared. So we have the moment of inertia. Okay, we're going to use all three equations. We have a center of mass that is stationary. Okay, so we're going to use equation 1714, where A of G in the normal and tangential direction are 0, normal tangential, so let's say normal down, and tangential up, or sum of force in the x and y direction, we can say. So sum of forces in the x direction is mass times acceleration of the center of mass in the x direction, and sum of forces in the y direction is mass times acceleration of g. That's an acceleration of g in the y direction. But those are 0 because center mass is stationary. Let's see what forces we have though. In the x direction, we have the friction force, and so we have friction force, which is normal times coefficient of friction. So kinetic coefficient of friction times the normal force will be this one, and then I have negative FAB times the angle here. Not the angle, but rather cosine of the angle would be same angle as here. So let's call this gamma, and this is also gamma. So FAB cosine gamma, and cosine gamma is going to be, I have 0.3, 0.4, and 0.5, so it's going to be 0.4 over 0.5, 4 over 5. 4 over 5 is cosine gamma. Right, so I have the horizontal force equals 0, and then I have in the vertical direction, I have normal force minus mg, and then minus there will be FAB sine gamma equals 0, and sine gamma is going to be 0.3 over 0.5, that is 3 over 5. Okay, so so that's for forces. Now we I overlooked. So there's another force. We need also the moment equation. So I overlooked in the positive direction of x, the F force, the 60. It's just 60 Newton force equals 0. Okay, so I have 1, the horizontal projectile of FAB, and this one, 3 forces. And in the vertical direction, likewise 3. So the weight negative and positive, and this one also negative. FAB projecting the vertical direction. Okay, so let's see how many unknowns we have. FAB, we have normal force, that is the first unknown. We have FAB, the second unknown, and then wouldn't that be enough? FAB. Any possible? Okay, so actually we need the moment equation just to find the initial angular acceleration alpha of the roll as the paper unrolls. Okay, so all good so far. We have the force equations. This allows us to calculate the normal force and the force in the bar FAB. So what do we have? It's the friction coefficient is 0.2. We have FAB times N. I have, and here by the way was a plus because 4 is the 60 Newton forces to the right. Negative FAB, 4 over 5 FAB plus 60 equals 0. And then below I have N minus M, mass is 20 kilograms, 20 times 9.81. This is 196.2 newtons, 196.2 newtons. Okay. And then I have FAB times 3 over 5. So 3 over 5 FAB equals 0. Two linear equations, two unknowns. We can solve for N from the first equation. So I'm going to change this to an equal sign. I make this plus, I erase the equal 0 part. And I'm going to substitute N in the first equation. So first equation was this, becomes 0.2 times 196.2 plus 0.2 times 3 over 5 FAB, the only unknown left, minus 4 over 5 FAB plus 60 equals 0. So FAB is 1. So FAB is the value 196.2 times 0.2 equals plus 60 equals, and then I have so this is 99.24, this piece and this piece, and then I have 0.2 times 3 over 5 minus 4 over 5 equals, so negative 0.68. Is it correct? So I have 0.2, this piece 0.2. Let's start over. 0.2 times 196.2 minus equals 0.2 times 196.2 equals plus 60 equals 99.24 positive value. Oh, of course, and this has to go to the right, so this is okay. And then I have 0.2 times 3 over 5 minus 4 over 5 equals a negative value, but because I moved it to the to the other side, it becomes positive. Okay, so the direction was correct, couldn't have been otherwise. So take the inverse times 99.24. So I have FAB equals 145.9 newtons. Okay, so I have this number, and this is good to now I'm good to calculate N. Okay, and the N is the important value in friction force from knowing N. Okay, so N equals 196.2 plus 3 over 5 times 145.94, value that we got. So times 3 over 5 equals plus 196.2 equals. Okay, this is 283.76 newtons, the normal force. So now I can calculate the friction force, because this one, it does moment about, we're going to some moments about the center of mass. So I have the friction force now, 0.2 times N, it's, so times 0.2 equals, it's 56.753 newtons. Actually, this one is of relevance. And the third equation, we're summing moments about the... Alright, so here's a problem. 1778 resembles problem 1780 that was assigned to you as a homework. And a good reference is sample problem 1710 on page 446. And I'm going to do the first approach. It's a bit lengthier, but to me more intuitive. Okay, so 1778. We're having the a disk. So what is this problem? There's a disk of mass 3 pounds, radius 0.75, and it's pinned at O, and there's a cable that runs around, and then one end is a 5 pound weight, the other one is 10 pound. Of course, the tendency for the, if released from rest, it's for the cylinder, the pulley, to rotate clockwise. We need to find the the speed of the weights after 5 seconds of being released from rest. Okay, cord does not slip, and there's no friction at O. So first, the mass moment of inertia of the disk. The information is available at the back of the book. So you either consider a thin circular disk, moment of inertia about z through the centroid is 1/2 mr squared, or a cylinder, mass moment of inertia about the z-axis and the longitudinal axis 1/2 mr squared. So it will be, in our case, 1/2 mass in slug, 3 pounds over 32.2, and then times the radius, 0.75 squared. Okay, so what is the answer? 0.75 squared times 3 over 32.2 over 2 equals 0.0262 slug foot squared. So we have the mass moment of inertia of the disk. Now, the approach would be that in sample problem. There's a sample problem that resembles this one here. It's on page 446, and I'm going to do approach 1, where we do separate free body diagrams of the 3 bodies there. So I have the disk, and there's the tension in the cable, T, B, and then there's the tension in the cable on the A side, and of course TA is going to be bigger. Then I have the 2 masses. Okay, so again, this is bigger, and the small mass and the big mass, and there's the weight, weight of B, weight of A. This is B, this is A, this is O. Okay. So intuitively, B will accelerate up and A will accelerate down. Because the cable does not slip and is inextensible, the 2 accelerations are equal, and they are related to alpha through the radius of the drum of the disk R. So what do we have? We have firstly kinematics. We have R. If we measure the angle, so R theta in radians is going to be displacement of B is going to be displacement of A. Of course, one with one sign, one with the other sign, but magnitude-wise, this is the relationship between them. So by taking time derivative, we get R omega is velocity of B is velocity of A, one up, one down, and R alpha is acceleration of B is acceleration of A is acceleration. We can call this V and A. It's so the problem says determine the Earth's speed. So we need to find V. This is what we need to find. Of course, the acceleration is also unknown, but we are asked to calculate V. Okay, so equation of motion for the disk, sum of moments about O equals I centroidal times alpha. And let's assume positive to be clockwise. So we have negative, or the positive TA. Let's start with A, TA times R minus TB times R equals moment of inertia about the centroid times alpha. And then we take body A and we sum forces in the x direction. Let's assume, or the y direction. So x and y. Sum of forces in the y direction equals mass of A times acceleration. And, well, since we took clockwise positive, let's take downwards y positive. So what do we have? We have WA minus tension A equals WA over 32.2 times acceleration. And likewise for the other body, so this was A, body B, sum of force in y direction is mass of B times acceleration. So we have, let's say, acceleration of A, acceleration of B. So we have, I said positives down, so there will be WB minus TB. It's understood that these are the same TB, three-body diagrams. Okay, so I said WB minus TB equals, and acceleration is up, it's negative WB over 32.2 times acceleration. Okay? And so the three equations, we have three unknown, oh, actually there are five equations. So first equation is R alpha equals A, first equation. And then we have the moment equation, and so four equations in total. Let's see how many unknowns. So there will be the tension in the cable on one and the other side, two unknowns so far. And then we have acceleration, and then we have alpha. So four equations, four unknowns. We are going to solve the problem in terms of alpha, or rather the A, I meant to say, so that we can then integrate and get velocity directly. We could get omega, we can go the other way. We can explicit acceleration A as a function of alpha, and this will allow us to, once we found alpha, we can get omega, and then from omega get velocity by just multiplying by omega by r. So which one would be, I mean, it can go both ways. Which one would be more, or make it slightly easier? Yeah, let's go the way I said. So I'm going to say alpha from the first equation. Alpha is A over R, and we have TA times R minus TB times R equals I O times A over R, and you know, we calculate mass moment of inertia of a disk, but what we could do is to just go as mass of the disk times R divided by 2. Okay, since this was R of the disk. Okay, just so I said 1 over 2 mass of the disk, mass of, let's call it D, times R. So this is equation, this is the equation. We can see that I have R that comes out, so it would be tension of A minus tension of B equals 1 over 2 W of the disk over 32.2. So the first, first two equations, we got, and of course there's A. How can we miss A? There's A here. Okay, so here's one. And then from, I'm going to explicit the tensions from the last two equations, TATV, substitute them here and see what we get next. So I have from the second last equation, TA equals WA minus WA over 32.2 times A. From the last equation, I have tension B is WB plus WB over 32.2 times A. Okay. And then these two substituted in the first or the equation that I'm just boxing gets us WA minus WA over 32.2 times A minus WB minus WB. This is D. WB. So I'm here and I'm subtracting. WB over 32.2 times A equals 1 over 2 WD over 32.2 times A. Okay, so this is enough to calculate A. Is it? Well, it cannot be but 0. Let's see. Have we missed anything? Actually, no. I'm sorry. There are two terms that don't multiply A, so it cannot be 0. So we have, if I move everything that's A to the left, I have WA minus WB over, it'll be WA plus WB, so I have WA plus WB plus 1 over 2 WD over 32.2. Okay, so we have acceleration A, and this would be constant. They're just weights, so it's not function of time. It's a constant acceleration problem, and we can calculate A. So A is with numbers now 10 pounds minus 5 pounds over. I have 10 plus 5 plus 0.5, 1 over 2 times would be 3 over 32.2. And let's see what we have. So it will be 10 plus 5 plus 1.5, 10 plus 5 plus 1.5 equals over 32.2 equals, I take the inverse and multiply by 5, and the acceleration is 9.7576 feet per second squared. So I have the acceleration. To get velocity, I would need to integrate linear motion. We've seen these equations before. We can use the answer here. So velocity is v0 acceleration constant times t. Okay, so v is v0 plus a times t. v0 is 0, so v is acceleration times the 0.5 second. So I still have this number, and I'm multiplying by 0.5, and it gets me 4.8788 foot per second, or feet per second. Okay, so this was it. The approach again was solution 1 approach, sample problem 1710. And this being said, I stopped the recording. Was 19 minutes.